Okay, a little bit on common raster data sets. There's a bunch of standard ones. Topos or topographic data sets, especially the 24Ks, are data sets we used to work with a lot. Nowadays, not so much, but they have a lot of detail on them, and if you're looking for historical data, they can sometimes be valuable for that. DEMS, digital elevation models, we use all the time. There's lots of them available, and we keep getting more, especially with LiDAR. Digital ortho quarter quads are old black and white images. They're handy because they go back into the 60s. So again, for historical data, they're good. Otherwise, NAPE has kind of taken over from the DOQQs, which are also color. Landsat, of course, we're headed almost 40 years of data with Landsat, depending upon which Landsat you're talking about. And it's amazing. 30-meter data, 7 bands, again, depending on which Landsat platform. All kinds of work can be done at this, even at global scales, to look at things like climate change impacts, agricultural changes, urban changes, all kinds of change detection going on. 30 meters, so it doesn't work for small extent studies, but large extent, it's amazing. And from Landsat, there's a number of different data sets. The most commonly used one is the National Land Cover Data Set, or NLCD. And again, this is one that you can do work just right off of the NLCD data. Like here we're showing the growth of a urban center displacing vegetation on the ground. MODIS is different from Landsat in that it's a lower resolution, 250 meters per pixel, but it's twice a day, where Landsat is twice a month. And MODIS is now the #1 source for tracking fires all over the world, actually. It's pretty cool data, and it has other applications because it's such high frequency. But again, low resolution. We tend to have that trade-off. We tend to either get high resolution or, I should say high spatial resolution or a high temporal resolution. You really can't get both because you just have so much data we couldn't process it all. And again, MODIS is being used heavily for looking at land change across the planet. Unlike vector data, which really has 2 file formats we use, shapefiles by far is the dominant one. Everyone uses it. It's open source. Thank you, Esri. And then we have CSVs, which we use for point data and field data collection, bringing data in from Excel. There's a few other vector formats, but they're not used very often. Raster file formats, there's over 100 that are used. It's a mess. These are some of the common ones. The 2 that I recommend using, in other words, as soon as you get data in Grid or Mr. SID or ECW, one of these other ones, just convert it to a GeoTIFF, which is a .tiff, and then internal to that TIFF file will be the geo referencing for the image, or an IMG file, which is the old Imagine file format. That's the most popular one used in ArcGIS and works the best, in other words, least amount of crashing. These are both good raster formats to use. GeoTIFF is used more in the open source community, so internationally, especially if you're going to work there. Image, if you're inside of ArcGIS all the time, it's the one to use. Just a quick note on some of these. The real issue with the file formats is sometimes you'll end up with something like a JPEG. Well, JPEG doesn't allow georeferencing inside the file, either do these files. So you may have a world file associated with it. Inside of that world file, there's the dimensions of the pixels, okay, and the coordinate of the upper left-hand pixel. And from those 2 pieces of information, really 4 because it's X and Y, the GIS package can figure out what the georeferencing is on an image. Now, it also supports rotation, but I don't know if I've ever seen an image that uses those. Often these will simply have a W, so JGW for a JPEG world file, or a TIFF-W for TIFF world file. The same rule applies when you're dealing with any of these files, is just take all the files that have the same file name, the prefix file name, the first name up until the first period. Make sure that whenever you're moving these data around, which is usually done in zip files, that you zip everything that has the first file name in it. Okay, ASCII file formats are kind of cool. It's not used too often anymore, but it's one that's actually ASCII or text. So you can just open it and look at it. Like, here's an example ASCII file that produces this image. It's pretty neat file format for that, and I use it in programming because we can look at it like that. Again, image and TIFF, both excellent choices for working with Esri. JPEG, you'll see it fairly often. We export our maps in it, but remember your map isn't georeferenced to the Earth anymore. It's just a map. It's intended to go into a report. So you don't see it too often. There is a JPEG 2000 that includes georeferencing inside the file, but it's still not as widely used 20 years later as JPEG is, the regular JPEG. So still good to just take them to image or TIFF, Imagine or TIFF, I should say. One of the very powerful areas where we work with rasters is doing what's called raster math, or raster arithmetic, and this is where we can take things like fuel density, slope, veg type, different hazards, and we can do arithmetic and come up with an overall fire hazard measured. And this would again result in a new raster. So we're doing arithmetic on whole rasters representing an entire area. Each pixel is being, in this case, added together. So a fire density hazard from one raster, pixels from that would be added to the pixels next one, and what comes out is then an overall fire hazard map. There's a whole bunch of different disciplines that use raster math, very commonly used. For an example, one thing you could do is, like, if we had a raster, here I'm just creating a random pseudo one, we could go ahead and add 12 to everything in it. And now we have a different raster. Now it looks similar because the rasters are almost always scaled to go from white being the highest value, black being the lowest value. So that's why these look similar. Okay, but see the values changing. And I'm going to go ahead and add a bigger number in. Okay, so these values are increasing because this scalar value has been added to each one of these pixels. Now, often one of the things we will do is we will take a raster like this, and then we will operate on it on this raster. And this is, again, it's important to note that we're taking this value, operating on this pixel to get this one. So it's a pixel by pixel operation. So in other words, if we go 98 plus 134 is going to be 232. Let's go and randomize this. Okay, and we do an update. We get 95 plus 31 is 126. So raster to raster arithmetic, producing a new raster. We can also do subtraction, and we can do multiplication, and we can do division. Okay, so we can do all kinds of arithmetic on our rasters between rasters. We can also compare our rasters. This is one that's, again, very commonly done. Like if you wanted to know which elevations were below a certain value, you could have a raster or a scalar value, either one, and say, well, which one is below a certain value? And out of that, you will get a Boolean raster. In other words, a raster with only true or false values in it. Now, they don't really put the word true or false into the raster. Instead, they put 1's for true, 0 for false. So here we can see that 200 is less than 225, so that value is true. 217 is not less than 200, so that value is false. And like with attributes and other values, we can do any of these Boolean comparison operators. This one is equals. It's equals because, well, equals would mean assign something, so they made it two equals. It's not great. Either is the exclamation point equals, which is called not equals. So it just reverses it. Okay? All right. So one of the areas that's pretty powerful is if you took two different rasters, like say you wanted to find out where the slope was over some value and aspect was within a certain value. You could say, well, let's find the slope over 10 degrees. That would result in a Boolean raster. And then you could say, well, where is the aspect between 90 and 270 degrees? And that would produce another Boolean raster. Then if you want to say, well, where is the slope greater than 10 degrees and the aspect is facing to the south, which is effectively what I did when I said 90 to 270. You could then AND those together and get the points where the slope is within a certain range and the aspect is also within a range. Or you could do where the slope is within a certain range or the aspect is in a certain range. Now this can apply to a whole bunch of things. This could be habitat. This could be area that's good for cattle and area that's good for elk. Where is good for both of them? Where is a habitat suitable for Doug fir trees, and for a marsh species. Different analysis for different types of applications. There is a function in ARC called con. It's conditional. There's a lot of other functions. This one I mentioned because it's powerful, it's commonly used, and it's confusing. Basically with con, what we're doing is we're taking a conditional raster, and that's one of these Boolean rasters, it's another word for it. And then we're passing in the value that we want the pixels in the final raster to take on for pixels that are true, okay? And then the values we want them to have when they are false. And the output of con is always a raster, but you can pass in a true raster, what I call a true raster or true scalar value, false raster or false scalar value. Okay, so whatever is happening in this raster, the pixels that are true here will get these values, the pixels that are false will get these values. Very important for things like being able to say, well, where is the stem greater than 1,000? And you could just have it put ones where it's greater than 1,000 and zeros where it's not. If you want to find out where the NDVI is less than 0, and then there you put zeros, and anywhere else you put the NDIV values. In other words, you just take the negative values, or values that are less than NDVI, okay, and set them equal to 0. Okay? All right, and this is on Raster Calculator with the old ARC map. I will do a new one with the new ArcGIS Pro. Check out the video here about uncertainty. It actually applies to anything. And then really quickly, these are histograms. Now, histograms are very powerful tools, especially when working with rasters, and you hopefully have already seen them with statistics. When we're working with standard deviation and normal curves or Gaussian curves, we're actually working with a histogram. In a histogram, you have buckets for values, and then on the vertical axis, you have the number of occurrences of each of those values in each of those buckets. So in this case, this is saying we have over 60,000 values in this raster that are 0, and then a much smaller number of between 0 and 15, 16 to 31, 32 to 47, etc. Okay, so it shows the proportional number of values within each bucket. Lots of zeros, not so much other values. Very important for us to be able to characterize things. Now here we get a different picture of it, because here I can drag this little box around and we can see how the values change as we move around the DEM. Okay, and very important for us to be able to do analysis of what is within pixels or rasters. Same idea for RGB images. They just don't sometimes load in Google for some reason. So here's an image of Humboldt Bay, a portion of it, and this is the histogram. Now, red is the number of occurrences of red, green is the number of occurrences of green, and blue is the number of occurrences of blue. So you'll see that there's relatively large number of blue values at 48, about 48, versus red and green, and then that changes as we move around. That changes over the whole image, the frequency of each of the colors. We can see that close up if we take and move this around. Lighter areas, this brownish area, there's kind of a distribution there, more even. Over here we get more greens, but also some blues. Here you might expect this is blue, but it's really got a lot of green in it too. So it's a way to analyze the contents of our rasters.